We recall from the previous video that we talked about examples of statistical or random sampling techniques. So we turn our attention to an example of non-statistical or non-random sampling techniques. And a quick example is convenient sampling. What is convenient sampling? Let's say here I am, and I've been told to choose a sample of units to represent this entire population. Now, if I decide to pick just out of ease of accessibility, to pick only these units to be in the final sample, what is the problem with this type of sample that I've chosen to represent this entire population? Did I hear you say that the green group was not represented in the sample? Yes. So this is the challenge we have with convenience sampling. The choice of sampling members is based on ease of accessibility or even selection, but most times it tends to be what? To be biased. So we take an example here. A student interviews classmates in his algebra class to determine how many pairs of jeans a student owns on average. Well, students in his algebra class are not the only students that exist. So this student must be using a convenient sampling plan because this is based on ease of accessibility and selection of fellow classmates was used here. So as it stands, this would be an example of convenience sampling. Now, just to remind us of some of the differences between statistical sampling plans and a non-statistical sampling plan like the convenience sampling, let's take some examples here. And we are to determine the type of sampling used. In question 5, a teacher puts students' names in a hat and chooses without looking to get a sample of 3 students. I would argue that that is a definite simple random sampling, a type of sampling plan where each and every member whose name is in that hat is guaranteed a non-zero but equal chance of being selected to be in the sample. Question 6. A principal orders t-shirts and wants to check some of them to make sure that they were printed properly. So she randomly selects 2 of the 10 boxes of shirts and checks every shirt in those 2 boxes. So every box here is a cluster. And so she randomly picked 2 clusters and decides to focus on those 2 clusters. This would be an example of cluster sampling. 7. A politician asks his neighbors their opinions about a controversial issue. Oh, just your neighbors? That would be convenient sampling. Question 8. A manager at a pizza shop wants to start visually checking finished pizzas, but she doesn't have time to check every pizza. She decides to check a random pizza in the first 20 made each day and then check every 20th pizza thereafter. I see 1 and then I see 20 jumps of every 20. Does this remind you of the systematic sampling plan? Question 9. A school chooses 3 randomly selected athletes from each of its sports team to participate in a survey about athletics at the school. Well, since they're selecting 3 from each of its sports teams, these sports teams will be each of the strata or each of the stratum into which the whole group has been divided, so that in each group they are more similar. Does that remind you of what we did when we worked with stratified sampling? So in this case, we would say that this qualifies as an example of stratified sampling. Then 10. A store prints a request on each receipt asking customers to fill out a satisfaction survey online if they are willing. Well, reaching out to your customers alone, that will be an instance of convenient sampling. Then 11. Each student at a school has a student identification number. Counselors have a computer generate 50 random identification numbers, and the students associated with those numbers are asked to take a survey. That is simple random sampling because it guarantees each and every student an equal chance or non-zero chance of being selected to be in the sample. Having discussed the different types of sampling plan, we now move on to what we call bias in statistics. What is a bias? It is an effect that alters a statistical result by systematically distorting it. It's sometimes a little bit systematic, not intended, sometimes almost subtle, and you have to be really mindful to be able to observe it. So, bias or problems that are associated with data collection can lead to fallacious results or conclusions being drawn from your data. So, there are four main data collection issues that are also called biases. You have interview or response bias, non-response bias, observer bias, and selection bias. Let's take one after the other. By interview bias, if you ask questions, let's say you're conducting an interview or an observation, the way you ask questions, if it prompts a respondent to answer in a certain way, probably out of fear or some other factor, then the kind of data you're collecting rather, is not factual data that really mirrors the true state of things. This will introduce some kind of bias into the results that can be derived from the data analysis. This is an instance of interviewer or response bias. Next, we talk about non-response bias. Non-response bias usually occurs if you're trying to study a population, for example, and some group who decide not to respond for one reason or the other have a different um, data that they would have otherwise contributed into your data analysis and results. In other words, you have decided to analyze just the results of those who responded. Unfortunately, the views of those who responded is quite different from those who did not respond. The original goal was to understand the entire population, not a sub of the population. So at the end of the day, you end up with some form of data that speaks to a particular subset of the population. And if you use that result to generalize to the entire population, you'll be coming up with with a result that is not valid. Then we talk about observer bias. For observer bias, for example, if different safety officers judge a safety worker on protocols differently, you have different data, different results. That difference in their data and their results and their conclusion, this is called bias. And so this kind of bias is bias introduced by different data collected on the same entity. Then next we have selection bias. If you use convenience sampling, you might end up with sample units that are not truly representative of the entire population. Now, if you claim that the results you got for the sample generalizes to the entire population, whereas the sample does not represent the entire population well, the result of the problem you have with that result of your data analysis is selection bias. So let's take some example problems to see how much we understand this concept. Question A. When people fail to respond to a survey, the data collection may suffer from non-response bias. That is definitely true. Question B. Data collected on the internet can generally be considered accurate since the data must go through a screening process before they can be placed on the internet. That is false. Anybody can type anything. The next question. Recently, an analyst in a company's manufacturing department surveyed customers regarding how often they buy a particular product. One customer indicated that she purchased the product 17 times in the last 6 months, but the analyst recorded the response as 71 times. This is an example of observer bias. That is not true. That is an error, a measurement error, not a bias. The last question, selection bias occurs when the respondent decides which of the questions on the survey to answer. Well, that will be an instance of non-response error, non-response bias, not selection bias. So this is a false statement. Now, as much as we have bias, we distinguish between a bias and an error in statistical analysis. An error in statistical analysis arises from the unrepresentativeness of the sample taken. So, if the sample you have taken does not truly represent the population or is not random, then what you end up with is two types of errors that we identify with in statistics, namely measurement error and sampling error. For measurement error, these are differences in data values based on how measurements were taken, probably in different ways or using different mechanisms on the same entity. Whereas for sampling error, if you pick a sample in a way that it is not random or it is not representative of the population, then you end up with different data values between what the sample units presented or gave us and what the entire population actually holds as facts. So this will lead to sampling errors. Now, associated with bias or errors, we can end up using statistics in the wrong way. And so we want to next look at how we can beware of bad statistical practices, such as graphical displays with poor principles of visualization. Let's take an example. These two are examples of plots gone wrong. What do you think? If you look at the y-axis here, this is 36, 37, 38. These numbers are very close to each other, whereas these are in jumps of fives. The tick marks are in jumps of fives. If you represent the monthly sales this way, just because the numbers are so close to each other, somebody might be getting fired here. So this is a dramatic and over dramatic representation of the data, as opposed to representing the same data in this way. So observe in this case that by having a poor scale on the vertical axis, the changes between the months appear to be more dramatic or exaggerated. That might lead to getting someone fired, and this might be misleading. So it is important when you are representing your data graphically to choose an appropriate axis or representation that does not overemphasize the facts or that does not under represent the insights in the data. Then again, look at another example. You have cholesterol levels for different patients. So you have different patients. What do you think is wrong with this? So you have each of these points represent the cholesterol level for different patients. What do you think? Since each dot represents an individual patient's cholesterol level, do you think these dots should be connected? Would that not mean that different patients' cholesterol levels are connected to one another? Is that an accurate representation of reality? The answer to that is definitely a resounding no. So, we now proceed to other ways, again, in which statistics can be misleading. If you take a sample size that is too small, it can lead to a misleading statistic or results. If the sample is biased, like you pick a convenient sample, or there is an outlier in the data, or there are incorrect calculations. These can all lead to misleading statistics. So let's take an example of a scenario. Jordan is collecting data from a random sample of 782 students at Northwood University and asked if they commute less than 30 miles to school. Based on the results, it reports that 62% of university level students in Michigan commute less than 30 miles to school. Why is this statistic misleading? What do you think? Well, what he has done is to generalize the results based off of the data analysis conducted for Northwood students to all university level students in Michigan. That might not be reasonable. In fact, it should not be done. So collecting data points from university students across Michigan would have been a more representative sample. We consider yet another scenario. Daniel asks 15 randomly selected students at Northwood University if they live in Midland. After, he reports that 71% of the students at Northwood University live in Midland based on a survey. Why might this statistic be misleading? Well, relatively compared to the size of the population of all Northwood students, a sample size of size 15 might be too small to provide a relatively good amount of information to get an estimate of the proportion of all Northwood students who live in Midland. So in this case, the sample size is too small. Then next, we proceed to the last example for this chapter. 75% more interracial marriages are occurring this year than 25 years ago. Why is this statistic misleading? Well, in this case, the baseline number of interracial marriages that occurred 25 years ago, 25 years ago, is a missing piece of information in this report. Because, for example, if 25 years ago it was just 2, then if it has increased to approximately about 3.5, that is 75% more. The use of 75% here more makes it look like there has been a huge jump. So this is more of a dramatic representation of facts. So we want to be sure that when cases like this arise, we ask questions for more data to see if there's a justification for the use of percentages here. With that, we come to the end of this chapter.